All right, welcome to Unit 2. This is going to be states of matter, and although you probably are familiar with the most common states of matter, I don't think at this time have a great molecular conception as to what makes each state of matter different. So what is it with the molecules that makes a solid different from a gas, different from a liquid? What actually are they doing that makes them different in identity, physical properties, and why are those properties so important in determining their chemical properties? So that's what we will try to attack here in Unit 2. And we're going to start out with solids and liquids. So first of all, let's address the phases of matter. Most of the matter on Earth falls into one of three obvious categories. You've got gases, you've got liquids, and you've got solids. And what's cool is that we've got such an interesting climate here on Earth is that we can kind of witness all three of these states at once in certain areas. For instance, in your kitchen, you have all three states of water. You've got liquid water out of the faucet, you've got ice in the freezer, and if you're boiling water for some noodles, you've got steam. So you've got all three phases of matter of water just in your kitchen. I think this is a really cool picture. This is actually this is argon, and if you look up the periodic table, it's on the far right side. It's a noble gas, and it's actually frozen. It's hard to see, but in this general area, in the bottom of the test tube here, you've got frozen argon, so ice, argon ice. And what's happening is, as we've taken it out of the freezing chamber, it's obviously starting to liquefy. So you've got liquid argon that's dripping out of the test tube. You can see that right there. Now, argon is a gas at room temperature. So as those little argon molecules fall through the atmosphere, they actually warm. They obtain energy from the air, from the surroundings, and they start to immediately evaporate. So you've got gaseous argon right there. So really kind of neat. In this small little picture, we actually have all three phases of argon. We've got argon solid, we've got argon liquid, and we've got argon gas. Pretty cool stuff. Now, interestingly enough, gases, liquids, and solids, if we add up all the gases, liquids, and solids in the entire universe, all of them, all of their masses, they won't equal the mass of the most abundant state of matter. We haven't even addressed it yet, and that's plasma. What the heck is a plasma? It's the most abundant phase of matter in the universe. Where do we see it? It's what makes up stars. Anytime you look at a fire, you ever sit around a campfire and you look at it and you think, well, what is that stuff? That's not a solid, it's not a liquid, it's not a gas, it's a plasma. Plasma is known as a superheated gas, and stars are made up of plasma. And as we look at this picture here, this is the Andromeda galaxy. This is our nearest galaxy to the Milky Way, to the galaxy we live in, which is the Milky Way. And the Andromeda galaxy is made up of hundreds of billions of stars, billion with a B. If you look at the center of Andromeda, you see it right there. That's just this massive clump of stars, billions of stars. Each one of them being about, on average, the size of our sun. And we know that we can fit about 1 million Earths into one sun. So just think about that. Each star that you're looking at there, hundreds of billions of them, we can fit about 1 million Earths into each one of those stars. And they're all made of plasma. So I think I may have just proven to you that plasma certainly is the most abundant phase in the universe. Now, all phases, gases, liquids, solids, they all have one thing in common. Their bits of stuff are always moving. Always moving. So let's address that. We're going to look at solids first. Solids do a great job at retaining their shape and their volume. If you have a solid piece of aluminum and it's a cylinder, you can easily find its volume. And it's going to stay a cylinder for a really long time. In fact, you're really going to have to change the conditions in order to change its shape. You'll have to exert a large amount of force on it in order to manipulate its shape, cut it in half, or bend it. Or you're going to have to try to heat it up, in which case it's no longer a solid, in order to bend it or misshapen it. We want to think of the stuff that makes up solids as little lumps. Okay, so I'm going to draw a couple little lumps here. We're going to make these guys orange because, we're the Panthers. So here we go. We got some orange lumps, and that's the stuff that makes up a solid. Now here's the thing with solids. If we take a look at our little sample, and maybe we take a little zoomed in picture here of just two of the little lumps. They're constantly interacting with each other. They should be about the same size, right? They're constantly interacting with each other. So at one point in time we see these two little lumps that are real tight with each other, but once they get too close, the little lumps try to repel. And then after a while they'll come close again. They'll attract each other. And then they'll repel again. So there's this constant dance between them, this attraction and this repulsion that they're feeling. Attraction and the repulsion. So this is the attraction, and then they repel, and then they attract, and then they repel. And we can think about this as kind of like a dance. You get close to your partner, you get farther away from your partner, and close to your partner, far away from your partner. But all along, you are connected somehow to your partner. And if we look at all of the little molecules in my circle here, they're all doing that same thing. They're attracting, repelling, attracting, repelling, attracting, and repelling. So these lumps are in this continuous dance. The repulsion and attraction to their partner is kind of like if they were attached with a spring and they were repelling and attracting and repelling and attracting over and over and over again. And that's very unique of solids. Okay? As a whole, if we don't just look at two little lumps, we look at all of the lumps that make up the solid. As a whole, these lumps make up what we call a lattice. Let's take a look at what a lattice looks like. Let's think about the red thing there being one type of lump and the purple thing being another type of lump. And they're constantly going back and forth. They're moving to and fro, back and forth, back and forth. But they constantly stay within a particular range with one another. And it's just not characteristic of this red lump and this purple lump, but it's characteristic of all the lumps in our lattice. So they all have this kind of attraction and repulsion for each other. They all kind of can form into a nice little crystalline shape, and that's how we produce our solids. They're very strong. They're tied and bound together one another. It's like this one big great dance. Now, we don't always have to say the phrase little lumps. Okay, that just sounds kind of unscientific. So let's see if we can change that around a little bit. Well, in Latin, little actually means, or cula means little. So cula is little in Latin. Mole is the Latin term for lump. If we combine the two, we will find the word molecule, which is Latin for molecule. There you go. So this big dude right here, this big solidified collection of little lumps is what we would know as a solid molecule. Okay? Kind of cool stuff. All right, let's go to liquids then. Liquids, certainly not as great at keeping their shape. They still have a definite volume, but we know that if we've got a liquid inside of a glass and your little sibling comes around and spills the glass, the liquid's going to pour out, and the shape of the liquid's going to change. Liquids always maintain the shape of the container they're in. However, the volume of that liquid will remain the same. If you had 100 milliliters in the beaker and then you spilt it, you'd still have 100 milliliters, but it'd just be on the floor. Now, what happens to the molecules? What happens to that little dance? Well, let's think about like a chocolate. Let's think of a chocolate bunny outside, because Easter's coming up, Valentine's Day's coming up, and you got this chocolate bunny outside on a day like today. It's going to be a salad because it's frozen, it's cold. But let's say you keep that chocolate bunny outside until May or June, and we have one of those really nice days in May or June where it's like 85 degrees. What's going to happen? Well, heat is going to speed up the dance of those chocolate molecules. So they're going to continue to repel and attract and repel and attract and repel and attract. But instead of that repulsion and attraction looking like this, that repulsion and attraction is going to start to look like this. The molecules are going to get further and further away. And pretty soon they're going to get so far away that they're not going to attract each other anymore. And they're going to be moving so fast that their speeds are not going to allow for the molecules to stay in that nice lattice shape. So heat has sped up the dance. The attraction breaks once the partners dance too fast. We can think about this as a molecular free-for-all. Now we've got all the molecules kind of like swimming in the pool in totally random directions. We've broken the lattice. When we break the lattice, we know that term. We don't call it, the ice lattice is breaking today. No, we say that the ice is melting today. And as I watch the weather, it looks like next Monday we should see some breaking of the ice lattices, finally, as the temperature is supposed to rise above 32 degrees Fahrenheit. So that's melting. So there's liquids and there's solids, right? Solids are just this uniform kind of construction, and liquids are the breakage of that uniform construction to get something totally new. I like this little cartoon thing. That ice cream is, in its solid state, it's a bunch of very, very tiny crystals, cream crystals. And the smaller those crystals are, the creamier your ice cream is. But once you take it out of the freezer, well, what do we know what happens? Those crystals, they absorb energy from the environment, and they start to dance faster. Those little molecules, those little lumps dance faster and faster and faster, and so our poor ice cream begins to melt, and we thus have to eat it faster. Ice cream.